In my last video, I looked at how to find the best reference image. Now we're going to look at an equally important task of setting the correct amount of gradient smoothness. Now this control shows the logarithm of the value. So a positive value is a high level of smoothness, and a negative value is a low level. Now we're going to be comparing the reference image with a corrected target image. So we can see the reference image here in the italic green font, and we need to select an image to compare it with. Now it's usually best to pick one of your worst images. If the correction works really well with your worst image, all the other images are likely to be superb. So we can sort on the noise column by clicking the noise header, and then we can select the image with the maximum estimated noise. So to select it, you just left click with the mouse. Right, we can now display the gradient graph dialog. So initially, this displays the reference image. If we untick the reference, it'll then show us our corrected target. And if we untick the gradient corrected target, it will show us our original target image. So we can see our original target image has a very large gradient in it. We're currently correcting it with the maximum level of gradient smoothness, which actually means that we're fitting a linear gradient as the correction. So we can see that that's helped a great deal, but it's not perfect. We can still see that the correction required more than just a linear correction. It's a more complex gradient than that. So if we now decrease the amount of gradient smoothness, we'll see that the correction ends up improving. And the value of the default value of the gradient smoothness control, that's been modified over time. So if you haven't done already, I would recommend that you reset the control using this reset button. And the new default is a much better starting point to find your best gradient smoothness. So if we now compare that, we're getting very close to an optimum solution. It is possible to go to extremely low levels of smoothness. And with this image, because it's not very noisy, because it was a 300-second exposure, we can probably get away with such small levels of smoothness. But we need to be very careful that we don't end up following the noise. So usually I would recommend a much smoother level than that. Somewhere between -3 and -2 is usually optimum. But you might need greater smoothing if you have noisy images. So the next thing I want to show you is looking at the actual graph to show you a graphical representation of the gradient that we're removing. So if I select the rejection circles and graph lines, we can see two green lines, and we can show a graph for the difference between the reference and target image along either the horizontal or vertical line. We can position these lines by double-clicking on the display, or alternatively, we can use the gradient path controls. So while vertical isn't selected, we can move the horizontal line. And likewise, if we select vertical, we can then move the vertical line. Well, let's start with the horizontal line. And if we tick on the graph, we'll see the sort of correction that we're getting. Now, the data points that have been plotted, these are the measured differences between the reference and the target. You can see it annotated there, one minus the other, along the line that we've specified. And we can see with large levels of smoothness that the line ends up much smoother than the points. And as we reduce the smoothing, we can see that the curve then begins to fit that line as well as we would like. So, for instance, at -4, we can see that the line then goes through all the points with great accuracy. And if we were to move our horizontal line, we can see how the gradient changes across the image. So if we increase our smoothness again, so we can see a smoothed image, you'll sometimes find that the line doesn't go through the center of the points. It sometimes goes above or below them. And the reason for this is what we were looking at before was the smoothing along the horizontal line itself. But now, when you're seeing a displacement of the whole line above or below the points, this is due to smoothness that's happening in the image's vertical axis. And then, because we're only plotting the points along the line, we're not plotting the points either side of the line, if there's a sudden change in the vertical gradient, that can shift the line away from the points. And again, if we reduce the smoothness, then it will fit the points exactly. So the main thing is, don't worry if the line ends up moving away from the points like this. It's simply to do with the fact that we're fitting a surface spline, and that's in two directions, not just the one direction we're plotting. So I think in this case, I would go with a correction perhaps like, I think 2.5 is probably a reasonable balance between fitting the gradient accurately, but not following the noise. Whereas I think -3 is beginning to follow the noise a little bit too closely. So we'll go with -2.5. Right, to return to our display, we can deselect the graph. And we can now do a compare with our newly decided smoothness value. Right, we can also, let's see if we make this display a little bit smaller and get rid of a few things. We can also change how the SDF is applied to our image, which may make it easier to see the gradients that still remain. So if we move the shadows to the right, that will give us more contrast in the background, whereas the control on the right-hand side is the image brightness. And then we can toggle between the reference and target, and we should see any differences in all their garish detail. And we can reset the SDF back to its default as well, using the button on the right. Right, there's one final thing I want to show you, and that's the manual sample rejection facility, the manual sample rejection circles. If we turn back on the rejection circles and graph lines, we can see that all the bright stars should have red rejection circles around them. And the reason for this is if we're unlucky and we have a bright star that's close to the edge of one of our gradient samples, the profile of the star could be such that some of that starlight might be in the neighbouring sample, some in the main sample. That in itself would be okay as long as the profile of the two stars is the same in both the reference and target image. But if the star profiles, for whatever reason, vary between the two images, we might get varying amounts of the starlight in one sample or the other in the reference and target image. So if we're unlucky, really bright stars could slightly reduce the accuracy of our gradient surface spline. So to avoid this, the program automatically finds the brightest stars and puts rejection circles around them. We don't need to worry about medium and faint stars. They don't have big enough profiles to cause trouble, and we don't want to reject too many of the samples. But here, because of my camera has blooming spikes, it hasn't recognized these brightest stars as stars, so these have been missed. On normal cameras, you may still have a problem if the stars are very heavily saturated, and that again can change the star's profile, and the star detection routine might miss them. So to add rejection circles for these stars, I've opened up the manual sample rejection section, and all we need to do is a control left click to add a circle. And then we can change the size of that circle by adjusting its radius. So that looks about right. Then we can add rejection circles for our other stars that we've missed. Now, if you end up placing one of the circles badly, like this one here, we can move back to that rejection circle and delete it and re-add it. So we can use the arrow buttons, and we can see that the currently selected image has a green circle instead of red. So we can now delete that and add it again. Now, when you're adding rejection circles, I'd strongly recommend you display the reference image, because if you don't, if you're displaying the gradient corrected target, every time you add a rejection circle, it has to recalculate the surface spline and update the display. And that might be time consuming. You might need to wait for the program to catch up before you can add the next circle. Whereas if the reference is displayed, it only needs to recalculate when we uncheck reference, when it actually has to display the corrected target image. So now it's doing just that. One final mention is this program has a really good track record for avoiding adding artifacts to the image. So unless you're using extremely small levels of smoothness with you should find that it's artifact free. If you've got satellite trails in the target images, you really don't need to worry about them. But it makes sense that when you're choosing the reference image, to avoid a reference image that has really bright satellite trails going through it. Right, so I hope you've enjoyed this tutorial, and please join me for the next one.